In this lesson, we'll learn about V-Ray subsurface scattering material, or V-Ray fast SSS2. And as we discussed in the translucency section of the V-Ray material, subsurface scattering is when light rays enter an object with translucency properties like candle, human skin, flesh, some type of fruits, milk, marble, and so many other things, then scatter inside the object and come out from a certain point from that object. First of all, I got a sore throat and a runny nose and feeling pretty sick right now. So sorry for the sound of my voice, but I gotta soldier through and record this tutorial and this lesson anyway. Now we are using the same scene from when we were discussing translucency in the V-Ray material. I've just changed the diffuse map for the backdrop material. If I go to the perspective view, this is the main light and it's coming from this direction, so we can see the scattering effect a bit better. And I have this fill light in front of the dragon with a very low intensity, just so we fill the shadows caused by our main light a bit and don't get any pitch black shadows. Now let's get back to our camera view here. Open up the material editor by pressing M, and let's add a V-Ray fast SSS2 material to our active view and assign it to the dragon model. As you can see, we have tons of parameters to control the subsurface scattering effect. Before that, let me show you two renders, one with a simple V-Ray material and another one with V-Ray fast SSS2 material. Both at their default states. I just increased the scale of the subsurface material to make its effect a bit more obvious. In the first render, a simple V-Ray MTL was used, and in the second one we have our fast SSS2 or subsurface scattering material applied to our dragon. And you can clearly see that in the first render we have an opaque surface without any translucency and light scattering inside the object. But in the second one, the translucency and scattering effect is quite obvious. Now let's get back to our material editor and check out different parameters of the V-Ray fast SSS2 material. Let me just arrange the frame buffer and the material editor a bit. V-Ray subsurface scattering material has three layers: a subsurface scattering layer, a diffuse layer, and a specular or a reflection layer. Subsurface scattering layer itself consists of two components: a single scattering component and a multiple scattering component, and together they create the final subsurface scattering layer. Single scattering occurs when light bounces once inside the material, and multiple scattering results from light bouncing two or more times before leaving the material. And if you take a look at the interface for the fast SSS2 material, you can see these layers and components. First, we have this general parameter. Next, there is the diffuse and subsurface scattering layers. We have our specular layer, multiple scattering layer, and some options to control the single scattering component and other things in the options rollout. In the general parameter rollout, first we have preset dropdown, and here you can choose different predefined presets for a set of translucent materials like skin, milk, marble, potato, and other things. You simply select one of the presets you want here and render the scene. I've rendered a few of these presets to start with. We have skin pink preset, milk preset, marble, and potato. So as you can see, it's very easy to get started and use one of these presets as a starting point for your desired material. Let me set the preset to something like marble and continue with the rest of the parameters. We have scale. if you come down to the diffuse and subsurface scattering layers, we have a parameter called scatter radius. And this value controls the amount of light scattering in the material. Smaller values cause the material to scatter less light and to appear more diffuse-like. Higher values make the material more translucent. Scale option here additionally scales the subsurface scattering radius, meaning if you increase the scale value, the subsurface scattering will be stronger and the material will look more translucent, and if you decrease it, the material will be less translucent and more diffuse. Also, the presets will change all the other parameters except for the scale here. Now, let's see a few renders with different scale values. In the first one, the scale was set to 1, then 3, 5, and finally 10. And as you can see, each time we increase the scale value, we make the material more translucent. For now, let's set the scale to maybe something like 5. Then we have the familiar IOR, or index of refraction of the material, which depends on the material you are trying to make. You need to search on the web and find the proper IOR value for the material that you are trying to make. Possibly 1.5 would be enough for most of what you want to create. For water-based material like water or skin, 1.3 would be good enough. In the diffuse and subsurface scattering layers, first we have overall color, which controls the overall color of the material and filters both the diffuse and the subsurface scattering color. Now let's change it to a purple color, like maybe 32 for red, 39 for green, and 130 for blue. And you can see the result of this change in the frame buffer. Now let me set the overall color back to pure white. Next we have diffuse color and diffuse amount. Right now diffuse amount is set to 0, so this material has no diffuse layer. By increasing this value, we are increasing the diffuse component of the material and at the same time decreasing the subsurface scattering layer. So at 0 there is no diffuse and only subsurface and specular layers. At 0.5 we have both diffuse and subsurface scattering, and at 1 we only would have diffuse. You can use any value between 0 and 1. And diffuse color, which specifies the color of the diffuse portion of the material. Now let's see a few renders with different diffuse amounts. First we have the diffuse amount of 0, which is our normal render without any diffuse component. In the next render, diffuse amount was set to 0.5. Now we take away some of the subsurface scattering and add some diffuse. And in the final render, diffuse amount is 1. And as you can see now, we only have diffuse and there is no translucency. Now let's set the diffuse amount back to 0, and as you can see, you can define maps to control these values if you want to. Next we have color mode, which allows you to determine the method to control the subsurface scattering effect. We have subsurface color plus scatter radius and scatter coefficient plus fog color. By default it's set to subsurface color plus scatter radius. In that case we have subsurface color and scatter radius to control the effect, and if set to scatter coefficient plus fog color, we should get a scatter coefficient and a fog color parameters down here. For whatever reason I don't get those parameters when I change the color mode, but I think in that case scatter coefficient will be the subsurface color and fog color would be the scatter color. Basically scatter coefficient would be the color just beneath the surface, and fog color would be the deep inside color of the object. It's really doesn't matter that much, as you would only need the subsurface plus scatter radius method to control the effect. But in this case, let me show you a render done with the second method. And as you can see, compared to the render with the first method, the result is very different. Now let's make sure the color mode is set to subsurface color plus scatter radius and get on with the rest of the parameters. We have subsurface color, which is the color for the subsurface portion or layer of the material. We have scatter color, which specifies the internal scattering color. Brighter colors cause the material to scatter more light and to appear more translucent. Darker colors cause the material to look more diffuse-like. Now let's change the subsurface color to a green color, like 58 for red, 124 for green, and 26 for blue. And as you can see in the rendered image, because we have no diffuse amount and the overall color is set to pure white, we get a very dominant green colored object because we have green defined as the subsurface color. Also, if I change the overall color to a darker gray, you can notice in the preview how it filters the subsurface color and makes it a darker, less saturated green. Or if I change the overall color to something close to a desaturated red, you can see how it filters that green color and alters it. Now let's set the subsurface color to its default value, and I'm gonna do that by setting the preset again to marble white. As I said, scatter color is the internal scattering color, and right now it's set to this desaturated orange color. And in the render, before we change the subsurface color to green, you can see a hint of this orange color spreading inside the object. Let's try a few other colors. In the first render, the scatter color was set to a desaturated red. The RGB values were 255 for red, 101 for green, and blue. And you can see this red color scattering beneath and inside the object. The next render, scatter color was set to a desaturated blue, and you can see the exact RGB values in the frame buffer. Next render, it was set to green, and finally a yellowish color. So that's about scatter color. We have scatter radius, and as I mentioned at the beginning of this lesson, controls the amount of light scattering in the material. Smaller values cause the material to scatter less light and to appear more diffuse-like. Higher values make the material more translucent. Let me reset the marble preset so we get our initial scatter color back. Now let's try a few different scatter radius values. In the first one, scatter radius was set to 0.5, then 1, 4, 10, and 20. As we increase the scatter radius, we make the material more translucent. Let's set the scatter radius back to 1. Next we have phase function. This value determines the way light scatters inside the material, and it can go from -1 to +1. And if I quote from Chaos Group, a value of 0 means that light scatters uniformly in all directions. Positive values mean that light scatters forward in the same direction as it comes from. Negative values mean that light scatters mostly backward. Most water-based materials like skin and milk exhibit strong forward scattering, while hard materials like marble exhibit backward scattering. In the first image, phase function was set to -0.9. Then 0, and +0.9. And you can see how this parameter affects the direction at which light scatters. Next, we have our specular layer parameters, and they should be very familiar. We have specular color, which is the color of the reflections, and you can choose any color here. Let's try a few color. Now let's set it back to white. We have specular amount, which controls the strength of the reflections or speculars. Even though we have no Fresnel option here, an automatic Fresnel curve will be applied to the reflections based on the IRR value defined in the general parameters section. Specular glassiness controls how sharp or blurry the reflections are. Higher values mean sharper reflections and lower values mean blurrier reflections. Specular subdiffs controls the quality of the reflections, and higher values mean more noise-free renders and increased render time. We have trace reflection, and if you disable it, only the highlights will be computed and the reflections will be ignored completely. And finally, reflection depth, which is the number of reflection bounces for the material. Now we have our multiple scattering options. Here you can define the algorithm to calculate subsurface scattering and related options to control the quality of each algorithm. First, you can define the algorithm or method to calculate the multiple scattering component of the subsurface effect. We have the default one, which is ray traced. We have pre-pass based illumination map and object based illumination map. Ray traced is using ray tracing algorithm to calculate the subsurface effect, and it is by far the best method and gives the most physically accurate results. And as you can see when set to ray traced, all the other options in this rollout are grayed out as they relate to the other methods and not ray traced. Pre-pass based illumination map uses an approach similar to irradiance map to calculate subsurface scattering, and like irradiance map, it needs pre-pass calculations. Object-based illumination map is similar to pre-pass based illumination map, but instead of relying on the resolution of the image to place the samples, uses the surface area of the geometry. Now let's take a look at 3 renders with different multiple scattering methods. In the first one, I used pre-pass based illumination map. The next one is object-based, and finally ray traced. Obviously, ray trace is the preferred method and it gives the most accurate results, but it also takes longer to render. In this case, the object-based method is very inaccurate, and if I compare the pre-pass based and ray traced method, obviously ray traced is more accurate. But at the same time, even though I use progressive image sampler with 4 minutes render time limit, but in the pre-pass based version, the render was finished in 2 minutes, but ray traced version surpassed that 4 minutes cap without achieving the desired sampling quality. So if you want a similar results without that much increase in render time, pre-pass based methods can be your choice, even though when you increase the quality of the pre-pass based method using pre-pass rate value here, you can increase your render time as well. As I mentioned, when the method is set to ray trace, there isn't any other option in this rollout. You have chose the best method and you are good to go. But let's set these to pre-pass based illumination map and see what we have. First, we have pre-pass rate. This parameter determines the resolution at which surface lighting is computed during the pre-pass phase. A value of 0 means that the pre-pass will be at the final image resolution. A value of -1 means that it will be at half the image resolution, and so on. Now let's take a look at a few renders with different pre-pass rate values. In the first render, pre-pass rate was set to -10, and we'll literally have no subsurface scattering at all. In the next one, it was set to -5. And still the resolution is very low and small that we don't get anything noticeable. In the next render, it was set to -1. And now we have our subsurface scattering effect, but we see noise in the effect. Then it was set to 0. And not only the noise has cleaned up significantly, we have more accurate results as well. Then it was set to 1, and finally 2. And as you can see, each time we increase the pre-pass rate, the quality and accuracy increases. And even when prepass set to 2, prepass rate set to 2, the render time is still quite better compared to the ray traced render down here. And it's a lot cleaner, obviously, but still ray traced is more accurate, even though still a bit noisy. Let's set the prepass rate back to -1. Next we have prepass ID, and according to Chaos Group, this option allows several very fast SSS2 material to share the same illumination map. This could be useful if you have different very fast SSS2 material applied on the same object, either through a multi-sub object material or inside a very blend material. If this value is set to 0, then the material will compute its own local illumination map. If it is greater than 0, then all material with the specified ID will share the same map. And the rest of the options here are for the object-based illumination map. So let's set the multiple scattering method to object-based illumination map. The main parameter to control the quality of this method is sample per unit area. It allows the user to control the number of samples that are going to be taken for each square unit of the geometry surface. As this method is very old and inaccurate, and it's here mostly for legacy purposes, I'm not going to explain its parameters by showing you examples of each one. I just quickly, I'm going to go over them, and you can try it on your time and see what each one does. We have auto calculate density. When this option is enabled, Very automatically assigns the number of samples to be used for each square unit of surface on the geometry. Enabling this parameter also disables the sample per unit area parameter. We have surface offset. To prevent artifacts, each sample is taken a tiny distance away from the actual surface in the direction of the normal. This parameter controls that offset. And if you enable preview samples, you can visualize the sampling done by the object-based illumination map. Sample color specifies the color of the samples. Background color is the color of the areas without any samples, and max distance is the radius for the circle that represents each sample. Let me just show you a render with preview sample enabled. First, let's enable preview samples, obviously. Change the sample per unit area to something like 6, and change the sample color maybe to a bright green. And you can see the render in the frame buffer and how the samples are placed by the object-based illumination map. Let's change the sample color to white again and disable preview samples. And finally, let's set the multiple scattering method to ray traced. Then we have our options rollout, and first you can determine the method to calculate single scattering. We have none, and in this mode there would be no single scattering component. We have simple, and in this method the single scattering will be approximated from the surface lighting, and its preferred choice for opaque translucent materials like skin. In the ray traced solid method, the single scattering component is accurately calculated by sampling the volume inside the object. This method is preferred for highly translucent materials like marble or milk, which at the same time are relatively opaque. In this mode, refraction rays won't be traced. We have ray traced refractive. It is similar to ray traced solid, but it also calculates refraction rays. This option is useful for transparent materials like water or glass. In this mode, the material will also produce transparent shadows. Now let me add a new untouched very fast SSS2 material and apply it to the dragon and use this material to see the difference between different single scattering methods. Just let me increase its scale to maybe 10 here. Now let's see how they look in the render. In the first render, single scatter was set to none. So in this one we only have multiple scattering. Then we have simple, ray traced solid, and ray traced refractive. And you can clearly see the difference between these methods. All of these renders were done with brute force as primary and secondary engines, these 4 renders that we had for the single scattering methods. Now let me set the single scattering method back to simple. Also let me assign our previous fast SSS2 material to the dragon. We have single scatter subdivs, and when the single scatter method is set to ray trace solid and refractive, this value controls the overall quality of the single scattering component. We have refraction depth, and this is the number of bounces for the refraction rays when the single scattering mode is set to ray trace refractive. Front lighting enables the multiple scattering component for light that falls on the same side of the object as the camera. And backlighting enables the multiple scattering component for light that falls on the opposite side of the object as the camera. And these two options became available when the multiple scattering method is set to a pre-pass based illumination map. So let's change multiple scattering method to pre-pass based. And let me show you a few renders with front and back lighting on and off. In the first render, both front and back lighting are off and we get no multiple scattering. In the second render, only the front lighting is on, and because the light that falls on the same side of the object as the camera is our fill light, we get a very small amount of multiple scattering. In the next render, only the back lighting is on, and because our main light is coming from the back side, we get a very strong subsurface scattering effect. And in the final render, both the front and back lighting are on, and we get a result which is the sum of the two. Let's make sure both front and back lighting are on and change the multiple scattering mode back to ray traced again. Next we have scatter GI. By default it's disabled, and when it is disabled, global illumination is calculated using a simple diffuse approximation on top of the subsurface scattering, and when enabled, the global illumination is included as part of the surface illumination map for multiple scattering. Obviously, enabling this option will result in increased render time and more accurate results, especially for highly translucent materials. In the first render, scatter GI is off, and in the second one it is on, and it's more accurate and more realistic compared to our previous render. Let me turn off scatter GI for now. Now let me quote from Chaos Group for some of these less important remaining parameters. Interpolation accuracy controls the quality of the approximation of the multiple scattering effect when the type is pre-pass based illumination map or object based illumination map. Larger values produce more accurate results but are slower to render. Lower values render faster, but too low values may produce blocky artifacts on the surface. Pre-pass blur controls if the material will use a simplified diffuse version of the multiple scattering when the pre-pass rate for the object lighting map is too low to adequately approximate it. A value of 0 will cause the material to always use the illumination map. However, for objects that are far away from the camera, this may lead to artifacts or flickering in animations. Larger values control the minimum required samples from the illumination map in order to use it for approximating multiple scattering. And cutoff threshold obviously specify a threshold below which specular reflections will not be traced. We got pre-pass mode, which allows the user to select the way the illumination map or pre-pass is used and reused. Single frame, when enabled, we will calculate a new illumination map for each rendering. We got single frame autosave. When enabled, Viri will calculate a new illumination map and save it in a file specified in the pre-pass file name down here. From file, when enabled, Viri is not going to calculate a new illumination map. Instead, it will use the map specified in the pre-pass file name to render the image. And we are having two fly-through modes to save and load the map when having an animated camera in the scene. And pre-pass file name, which specifies the file name of the illumination map to be saved in or read from. Finally, we have our maps rollout to add or adjust any of the parameters in the above sections, or in case of bump, opacity, and displacement, you can define maps and textures and control those effects too. For the final render, let me change the scale to something like 4. Let's make sure scatter GI is enabled. Now let's take a look at the final render. I also have the denoiser pass defined in the render elements and set its preset to mild. So let's see how it looks. We get this beautiful material and render, and it's almost the default state of the marble preset with just a few changes. You can also right click on the image and select load render settings to see what render settings I use for the final render. So in this lesson, we learned about V-Ray subsurface scattering material or V-Ray fast SSS2. Hopefully you learned something, and I will see you in the next lesson.